I'm gonna go upstairs.
Okay, bye. Okay. So we relate this to positions on a circle, the cyclical motion. So 1/4 corresponds, 1/4 t corresponds to 2 pi. Over here, right, the motion is at pi, and this corresponds to 1/2 t, right? 1/2 way around. And if you look at it, we're on the opposite side, right? We're now, instead of being above the equilibrium position, we're below it. And at this point, we start moving in the opposite direction. And if you look, we go around the circle like this. At this point, we're moving downward. So it's very analogous, right? And this is 1/2 t is equal to pi. And we go around, and then we have 3/4 t, and that's equal to 3/2 pi, right? So we relate this motion to circular motion, right? And we can do this because the sine and cosines. And this is how we'll describe it, right? So really, this angular velocity really applies. This is really angular velocity, like as if you're going around in a circle, right? And it's multiplied by t, and so we scale t according to omega. Omega is much larger. You'll reach this value will reach 2 pi much quicker, right? Or this value will reach 2 pi much quicker. Now let's look at this phase, or let's look at this phi term. What is this? Well, phi in this case is just a constant. It does not depend on t, but this tells us our starting position. Did we stretch it up? Or did we start when it was down? Here, if we start when it was up, phi would be 0, because that corresponds to the 0 point on the circle, right? When cosine is the largest, our x is the largest it could be, right? So at t is equal to 0, we would have to set this equal to 0 to start at this point. What if we started, like as we did in the previous drawing, downwards? What would phi be then? Well, at that point, t is equal to 0, right? But this cosine function will have to correspond to pi, right? Because we're starting at the negative equilibrium position. So this would have to be negative. Sine would have to be 0, of course, again. The velocity is 0 when it's at this point, at the low max. So we set phi equal to pi over, is equal to pi here. So this is known as the phase. It tells you what, at which point in the cyclical motion you start at. Hold on, guys. I'll be. Okay. Let's continue. All right. So we have. All right. So we have these terms inside of the trig function, right? And this tells us where we are along this position, right? Now this distance is a, right? So what happens is that, right, we have our amplitude, and this cosine and sine function varies this amount, this amplitude, from 1 to -1, right? From a to -a, right? Because cosine and sine is just from -1 to 1. So with this will vary the amplitude between these two, between -a and a, right? A is just a scalar quantity. Describes how much we stretch off the spring. And inside this integrand describes where we are along the cyclical motion. Do we depress the spring all the way down to -a, right? That would correspond to this whole function being equal to pi, right? And so on and so forth. Are we at the equilibrium position? Well, that would correspond to this cosine function being at either pi over 2 or 3 pi over 2. And we see that the sine function, the velocity, varies differently than the position. We see that what it is it's wherever the cosine is at maximum, the sine is at 0, and vice versa. And this really describes the cyclical motion that way. Now, for this, right? So let me redraw this motion. So let's say we have the position function. X is drawn in black. Right? And then let's draw the velocity. Well, the velocity is a sine function. So at 0, assume that the phase is 0, right? We see x is at a peak, so the phase is 0. Right? At 0, we start at 0, so there's no phase term that we need over here. Well, if we look at it, the sine would be 0. So what ends up happening is this. And this is the velocity. Can you see that? Okay, great. So the lighter color is the velocity, right? And what we say is that the velocity is 90 degrees out of phase with the position, right? If we just kind of translate this function over by 1/4 the period, or pi 1/2 in terms of a circle, they will overlap and they'll match up, right? So we say that the velocity is 90 degrees, or pi over 2 out of phase with the position, right? And this corresponds to a cosine and sine. Cosine and sine functions are 90 degrees out of phase, right? You have, remember this identity, cosine theta, or we'll put theta, is equal to sine theta minus pi over 2. Right? It satisfies this relationship. This is supposed to be a pi. So when we say things are out of phase, we mean that it's translated separately. Now, if we look at if we look at the acceleration now, well, that's just negative. That's just the negative cosine function, right? So here we start at the max, and it'll look something like this. And for this, let me. So for this, the acceleration, whenever the position is at its max height, the acceleration is in the opposite direction. And what we say is that this is pi out of phase, or it's completely out of phase, right? Because whenever this has a max, this has the negative max, right? Negative a omega squared. So this is completely out of phase, is what we say, or pi out of phase, or 180 degrees out of phase. This is the terminology we use, right? And you know, and that this describes that, oh, it's the same type of motion. It's just we just translate when it has the max and min. Right. Now, to determine the phase, or when you start, or not the phase, to determine the phase, or to describe how you start, what we say is that these are the initial conditions of the oscillation. Okay, how do we start this oscillation? Do we lift up the spring and then release it, and then that's when we start counting, we start the clock? Or do we pull it down? Do we start at the bottom and then release it and start from there? Or do we start it from the equilibrium position and just give it an impulse of force to start this oscillation? That's where the phase. That's where you determine the phase, right? Here the phase is 0. If we started at the bottom over here, the phase would be pi, right? Because t is 0, so this would have to start. This would have to start at pi. Or do we start somewhere where we provided an initial impulse of force to get the object in motion? And in that case, the t would equal 0, so this term is 0. But we would start at this point, so this would have to correspond to pi over 2 or 90 degrees. That's how we determine the phase. So there's really 3 quantities that describe this angular, these oscillations, or simple harmonic motion. And that would be the amplitude, how high does it go back and forth? Omega, how fast does it move? Does it repeat this motion? And then phi, where does it start from? How do we translate this sinusoid to match our initial conditions?
Negative,
Yes.
right?
What's up?
It could be negative on where it starts.
Yes. If we start down here, how do we satisfy this equation? So if we start at negative a, right? Well, t is 0, right? Where our starting point, we usually start at t is equal to 0. So then for it to be negative, what does phi have to be equal to? What makes a negative, what value for cosine do you get a negative 1?
It was 90. I'm not even sure.
It would be at this point. What angle corresponds to this point on the circle?
Oh, pi?
Pi, exactly.
Right.
This will give you a negative 1 for cosine, right? So you would just set phi equal to pi. And they'll give you a problem like this, like, oh, we pull the spring down, we start the motion from there, so then you know that you start from negative a, and then so then you know phi. Let me see. Okay. And in the book, they call this the phase angle. Which most physicists just call it the phase. They drop the angle term that's assumed. Right. Now, let me make one more remark about the trig functions. So what are the units inside this trig function? So let's see. So we have omega.
Hello?
Yes.
Oh.
So we have omega. That's radians over s, right? Because the frequency is 1/seconds per second, how many times it occurs per second, times seconds. And this is just an angle, so it's radians. So here, the two s's cancel out. So then the angle, the units that we use are this radians. And remember, radians is not an actual unit. There's nothing physical about it because it's a ratio between two distances. So inside a trig function, there are no units. If you get units in the end, if you get some kind of physical unit, whether it's length or time, that means that you didn't plug in the values correctly. Right? Now, okay, so I'm going to erase this. Let me see. What should I erase? Let's erase this. Now here I didn't draw it. Well, I did draw it a little bit differently, but the amplitudes for the velocity, for the position, velocity, and acceleration are slightly different, right? Here the amplitude is just a. Here it's a times omega. Here it's a times omega squared, right? So that V max here is just a omega square, a omega. A max is a omega squared, and then here x max is just a. Now, now if we start from this equation, right? Omega times t, 1 full revolution. This is equal to 2 pi from that circle, right? So that means that the period is just 2 pi over omega, right? Then, if you remember, the period is equal to 1 over the frequency. Remember that omega is the angular frequency, right? It's a little bit different than just the frequency, just how many times it occurs in a second. It's a little bit different because we multiply this by 2 pi. And if we look at the frequency, how many times it occurs in a given amount of time or a second, it's really, the period is related like this. Now we can relate omega and f. So omega is just equal to 2 pi times f. We get these two equations to relate it, right? And you could, I just used this interchangeably, the angular frequency and the frequency. You just got to remember that you got to multiply this 2 pi to go from one or the other, or divide, depending on which way you go, right? Now, and it's important to note, when do we have simple harmonic motion? What type of force do we need for simple harmonic motion? Well, what type of force did we get with the spring? Well, with the spring, we had this, right? The m times the acceleration is equal to kx. So you'll always have simple harmonic motion when you have a linear force, what's known as a linear restoring force. So whenever you have this linear force that wants to bring it back to a certain position, this restoring force, and it's linear, you get that differential equation that solves for this, right? So you have to have this linear force, right? If it's x squared, that's not linear. It won't satisfy simple harmonic motion. It'll repeat itself, but it won't satisfy this sine and cosine function, because you'll have cosine squared, right? So the whole key is whenever you have this linear force, you'll get all this beautiful behavior. Now, let's take this spring again. Let me ask you. Let's say I want to stretch it even more. Let's say if I stretch it double the distance that I did in the previous problems, right? And then it goes down here, right? Will this oscillate faster or slower? Anybody? Will this move fast? Will this complete one cycle faster or slower?
What was that on the far left?
This?
Yeah.
Oh, the starting position. We lift it up and then we drop it from a much higher height than we did previously. What will happen? Well, if we drop it up higher, when it reaches this point, it's moving a lot faster, right? When it's reaching this point at pi over 4, it's moving much faster, right? Because we're dropping it from a much higher height, and then it'll stretch down. So the forces are greater, right?
Yeah.
So would this translate to a faster oscillation? Or we should really say omega. Will omega be larger? You think it'll move much more rapidly up and down?
Yeah.
It'll repeat itself in a different amount of time, right? It makes sense, right? It's moving faster, right? Well, let's see. Let's look at the equations. Do you remember what omega is equal to satisfy the differential equation? Let me write the differential equation up here. Or I just want to write it in a place where I don't have to erase it. It's hard with this small board. So we have this, right? Kx squared, right? And then we found out that when we solved it before, we found that omega, the angular frequency, what did it depend on? Right? To make this, plug this in and satisfy it over here, and plug this in and satisfy it here, we set the value for the frequency, right? And if you remember, that corresponded to K over M, right? So this corresponds to how fast it oscillates, right? What is K over M? What is omega's depend on? It only depends on K over M. Does it depend on the amplitude? No. So it doesn't matter whether I stretch it more or less, it'll oscillate at the same frequency. That's kind of cool, right? Well, and if you think about it, why is this the case? Well, I stretch it up more, it picks up a higher velocity over here, but it also travels further, right? It'll happen that how much velocity, how much you increase the rate of motion and the distance that it travels, it ends up compensating for each other. So the period does not change, and neither does the frequency, how fast it oscillates. And this is really important, right? This allows us to make clocks very easily, right? Because it doesn't matter. So if you take let's say if you take this pendulum or this spring, right? And your unit of 1 second corresponds to 1 circular motion. And you just count how many times this repeats, right? It doesn't matter the amplitude that you start at, so it's easy to get the same frequency or period or the same second every time, right? Because it just depends on the spring and the mass, and you know, as long as you set it in the beginning, it doesn't really change that much, right? And we'll see that's the same case for the pendulum. It doesn't matter how much you start the oscillation back and forth for the pendulum, it'll oscillate at the same speed. Now we did kinetic energy, right? The energy. So well, let's go over it one more time, or let me write it down. So for a spring, we'll consider a spring, the energy corresponds to this, right? Its position and its velocity, right? And when it's at the top, at t is equal to 0, let's say for this case, E is equal to this, just the amplitude, right? Hey guys, in 10 minutes, the second Zoom meeting will end, and we'll take a 5-minute break, and then I'll finish the rest of this chapter. So we'll have this, right, at t is equal to 0, and then at t is equal to, t is equal to 1/4 the period, right? That corresponds to equilibrium position. we'll have the energy all in the kinetic term. I wrote this down before. V max, right? And we'll see that based on the conservation of energy. So let's find out what V max is, the maximum speed. Well, we just got to set these two equal to each other. Right, we have E0 and E1/4. Right, we have this with conservation of energy. These two positions are equal to each other. We set it equal, and we find that V max is equal to K over M A. Right? This is V max. Now let's relate the velocity at any position to its maximum to the position NA. And then this is just equal to omega A. And this is what we had from before when we took the second derivative, right? And really this is plus or minus, right? Because we take the square root, so it could be plus or minus. And it's oscillating back and forth, right? So it does experience both velocities. And using this equation, and more generally, let me write it over here. More generally, we'll have this. At any given position, x squared, and this is just or this k. This is equal to ka squared, right? The energy at any given position is equal to one of these extreme points in the oscillation, right? And then if we solve for v in terms of x, we'll find that v max that the velocity at any given point is equal to this. Just the position 1 minus the position over A. Okay. And this is just another approximation, really, for a sine function. So if we take this motion, let's see what happens with this motion, right? Let's graph out the potential energy as a function of distance. Right, this is 0. Well, and this is energy. And what happens is that over here at the top, it starts out with a lot of potential energy. And then the potential energy drops and it raises back up, right? And it takes this parabolic form. And then the energy is just at this point is 1/2 Ka squared. And what happens is that we see a transfer of energy occur between the kinetic and its potential energy. So at the top, this is all potential energy. Or I should write this. I shouldn't say at the top. At its maximum position, whether you're at minus A or max A, you have the max kinetic, max potential energy. And then as it drops, that potential energy drops and it gets transferred into kinetic energy and then back again on the other side to potential energy. And what we say is that underneath the curve represents the potential energy at any given point, right? This corresponds to the U in the system. The area underneath the curve corresponds to the U. And then this part like that. This corresponds to the kinetic energy. So this area corresponds to the kinetic energy. The area that's constrained is at the max energy, right? And if you look at any given point, the U plus the K is always equal to this line, right? At any point along the motion. Now, if you look, this is a stable equilibrium point. 0 is a stable equilibrium point. You move it away, it will want to come back to 0, right? If you have a ball over here and you drop it down, it'll roll back and forth, right? It's always good to look at this energy curve as hills, or a gravitational potential energy. It's just very easy to imagine and use as an analogy. So if I drop a ball over here, I'll just roll up and down this hill, the two hills, right? Then at 0, it's the maximum velocity, and that will go under simple harmonic motion. Okay, we did 14.4, where we described it in terms of circular motion. So let's go over the pendulum.
It's about to end, Professor.
Yeah, it's about to end. Yeah, I was thinking the same thing. All right, we'll start in 10 minutes, guys.
All right.
Okay?
Copy.
All right.